Hello there, welcome to section 3.3 out of your textbook, where we will be addressing the International System of Units. So we're going to open up with a quote, a little bit of science history here. This quote comes from Lord Kelvin, the guy for whom the unit measuring temperature Kelvin is named. He was also known as William Thomson, and he was one of the founders of thermodynamics. And get ready for this scathing quote. Try not to be too upset. Don't get too triggered at what this rude guy said. He said this: I often say that when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. I'm literally clutching my pearls right now. This is so offensive. Your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever the matter may be. Now, this sounds like a comment coming out of some degree of elitism, but this guy is absolutely correct. Again, remember that the founding fathers of science, these guys were obsessed with the idea that humanity's cognitions were significantly impaired by the Adamic fall. And they said, and they really taught us to be skeptical of claims that we might make. So they really pushed this idea that if you're going to make a claim about the natural world, then you better have a measurement or a formula. You better stake that claim on measurements. And really, I think this is actually what makes for really, really good science, is this very thing. So let's move on. So in the world of physics or chemistry, physical quantities are measured using an accepted unit of measurement. So nowadays, we don't accept cup. We don't accept cup, teaspoon, or tablespoon, or gallon as units for measuring volume. We just don't accept that. We accept what's called the meter, liter, gram, the metric system of units. And these are fundamental units, and the fundamental units are the result of direct measurement, such as meter, liter, and gram. And what I mean by direct measurement, you will learn in the next slide, is that meter really does mean something. It is a unit that is literally the result of a direct measurement, as is liter, as is gram. Now they say gram, I really think it's kilogram. Kilogram should have been the term put in there, but I digress. Derived units are the arithmetic combination of fundamental units, like cubic meter. What is a cubic meter? It's a meter times a meter. What is a newton? I hope you guys know what a newton is. A newton is a unit of force, and it takes into account the mass, a kilogram of something, times the acceleration. Good Lord, acceleration is a derived unit. Acceleration is meters per second squared. So a newton, very much the derived unit. Or joules. Joules is also a derived unit as well. Joules is a newton meter. And a meter is not a derived unit, but the newton is. So we use all kinds of derived units, but know that derived units all have as their basis some fundamental unit. Now, the meter, I told you that the meter was a very distinct measured unit. It's the SI unit of length, and it's defined as the distance light travels in 1 over 299,792,458th of a second. Okay, that's how far light travels. Okay, and for us, it's about 39.37 inches. Okay, that is the unit of a meter. A kilogram is a Système International unit of mass, and is defined by a cylinder of a platinum iridium alloy, and it is kept at the International Bureau in France. And this physical thing, this physical cylinder, is actually the basis or the standard by which we get kilogram from. Okay? And then if you look at second, This is fun. This is the SI unit of time, defined as 9,192,631,770 vibrations. It's how long it takes for this many vibrations of the cesium, it's the isotope cesium-133 atom. Okay? Don't ask me how anyone came up with any of this. I don't know why. But there you have it. These are actual meter, kilogram, second. These actually are fundamental units that denote a very specific measurement. Okay? So here's a data table. This is in your textbook. And in this, I'm sorry, it's not a data table. It's a table of commonly used prefixes that we use in the metric system. And these are the prefixes that are often tagged on to one of these units, okay? And you see the symbols here, the symbols in the furthest left column, and then you see the prefix, the factor, what that is mathematically, and then how to write that particular thing in scientific notation. So you know a capital M is a mega. A mega is worth 1 million. To reflect that in scientific notation, it's some unit number times 10 raised to the 6th exponent, to the 6th value. Kilo, if we were, and how do these combine with like these units of gram, meter, or what was the third one? Or second. I mean, you don't ever say a kilosecond. But, you know, we are all familiar with this idea of kilogram or a milligram, or in terms of meters, we're all familiar with nanometers or picometers, millimeters. We're all familiar with these. So you typically tag a prefix, you know, one of these prefixes that's used in the metric system, and then we add it to the measurement that we are taking. One of those fundamental units here. So here's some additional ones. So for length, we want to use the unit of a meter, and there's its symbol. For mass, we might use the unit of kilogram. Now you're going to realize later on that maybe grams is going to be a more important unit. Just regular grams. Time is second. It's an S. Electric current. I don't think we're going to be really using electric current or luminous intensity for that matter. In this course, electric current is an ampere, or capital A. You guys all have a pretty good idea of what an electric current is from your conceptual physics. Temperature is measured, the fundamental unit is Kelvin with a cap, or we reflect that with a capital K. We will use Celsius in this class a lot, and Kelvin at times. Never, outside of doing conversions from Fahrenheit to Kelvin, we'll never use Fahrenheit to measure anything in this class. We will snicker and laugh mercilessly at measurements that are made in Fahrenheit. Amount of substance is a mole, and then there's the symbol MOL. And what is a mole? Well, a mole denotes how many particles how many particles of a pure substance are representative of, like for example, carbon has an atomic mass of 12 atomic mass units. Well, if I wanted 12 grams of carbon, I would have 1 mole, which is equal to 6.023 times 10 to the 23rd atoms of carbon. Now, you don't have to worry about this all right now. We're going to be getting into what the measurement of a mole is, I think, in chapter 5. But just know that mole is, you can look at mole very much like a dozen. A dozen is exactly 12, okay? So a mole is exactly 6.02 times 10 to the 23rd count, and it's a count. A mole is a count. And then don't worry about candela. I never even knew what candela was until I taught this class. So here's a homework question 17. Name the quantity measured by each of the following SI units and provide the SI symbol of the unit. So we have a mole. What's being measured with the mole, y'all? How about kilogram or cubic meter? What's being measured? Second, Pascal. Okay, I don't think we'll even really use Pascal in here very much. That's like an advanced physics number. And then, of course, meter. So what are you being measured? What are you measuring with the mole? What's the quantity measured? You are measuring, and kilogram. How could I forget kilogram? Good Lord Almighty. So when you are measuring something using the term mole, you are describing the amount of a substance, and the SI symbol is MOL. What about kilogram or cubic meter? What are you measuring? Or cubic centimeter, does that help? You are measuring, well, you can use, I'm sorry, it's kilograms per cubic meter. I'm sorry, it's kilograms per cubic meter. That is the density of a substance. And the symbol is rho, and is expressed by the mathematical equation of kilograms per meter cubed. Okay. What are you measuring with second? Gee, I don't know, is that temperature? No, it's a time measurement expressed as seconds. Pascal is a measurement of pressure expressed as PA. Meter, you better know this, it's measuring length expressed as M. And then, of course, we have kilogram. You are measuring the mass of a substance, and it's expressed as kg. What I'm really disappointed that they did not get on here was volume. So volume would be a cubic meter, cubic centimeters, or a liter. I'm surprised they didn't put that. Okay, we have homework question number 19. So it goes something like this. What is the symbol and meaning of each prefix? So we have a milli, a nano, a deci, and a centi. So what is the symbol for each one of these? Well, for a milli, it's a small m, and a milli is 1,000th of something, okay? And then we have a nano with a small n, and a nano, I think, is 1/100000th of something. It's 1 times 10 to the negative 9. A deci, what's a deci? We, by the way, will never use deci in this class. A deci is represented by a small d, and that is 1/10th of a unit. And a centi is a small c, that's 1/100th of a unit. Okay, we'll probably won't use centi much in this class either. So how many grams are in each of these quantities? We have a centigram, a microgram, a kilogram, and a milligram. So in a centigram, how many grams are in that? Well, a centigram is 1/100th of a gram, and rightly represented as 0.01. A microgram, what's that? I think it's a millionth. It's, yeah, there it is right there. It's 1/1,000,000th of a gram. And we could be using micrograms in class. For calculations, I mean. A kilogram, kilo means refers to 1,000 units. So a kilogram is 1,000 grams. And a milligram is 1,000th, okay, of a gram.